All right, now we're going to practice using the Bernoulli equation for a couple of situations, illustrate some times when it is used and can be useful. We're going to imagine first this pipe. This pipe is going upward at an angle, so the water is water. So this is water flow. The water flow is going up the pipe so that it's being more and more elevated as it goes through the pipe. It's traveling at a uniform velocity of 12 meters per second. Now, first thing that should jump to mind right here is, is that realistic at all? That inside a pipe, the water would be traveling, all at 12 meters per second. We know at the walls that the velocity of the fluid is going to be 0. So again, it really depends on the diameter of the pipe and the length of the pipe as to whether that's going to be valid at all. At some point, it is not going to be valid. There are going to be frictional effects creeping into that pipe. But there are times when that pipe flow, if the pipe is short, that we can treat it as a uniform flow, in which case viscous effects are not significant. The viscosity effects have not reached into the center of the pipe. So we'll see how that goes. We know the pressure outside is 101,000, just one standard atmosphere, newtons per meter squared. And we know the pressure in the pipe at a particular point right here is going to be 120 kPa, so that's 0.1. And and you're asked to find the heights of all these different tubes that have been poked into the pipe as pressure measurements. So if you look at this H1, well, that's going to measure the pressure. These pipes are all open at the top to the atmosphere, so that's going to measure the pressure difference between the atmosphere and this 120 kPa right here. So that's what that's going to do. So we can figure out that H1 pretty easily based on our hydrostatics. This pipe, as you notice, very intentionally drawn so that its inlet opening is facing the direction of flow. So the velocity of the liquid that's going to that pipe is gonna be reduced to 0 right in the entrance, right? Because the flow will reach some height here and then it will stop moving. So the fluid right at the entrance to this little pipe is moving at 0 velocity. And so that's going to cause a change in the measured pressure. We'll see that as an effect of the Bernoulli equation. So the Bernoulli equation tells us that this grouping here is going to be constant. If that V drops to 0, something has to increase. And obviously, it's not going to just jump up in the air. That's what this would be doing. What's going to have to increase is that pressure is going to have to increase to make up for the fact that this velocity has dropped from 12 meters per second to 0. So that's going to allow us to make a determination. We're going to see that height is different because of that than this height because of that difference in velocity. The fluid traveling past this opening is just traveling at 12 meters per second. This H1 opening, just zooming right by at 12 meters per second. But the fluid trying to enter the H2, it's going to have to stop because the opening is facing the fluid. At H3, of course, we're back to just an opening that is facing upward. So no velocity into that opening, and it's just going to go by at 12 meters per second. So we'll see what the pressure is up here. Have to figure out that. And then it's the same thing here. We have an entrance that's facing the flow. Velocity is still 12 meters per second. So we're going to see, again, a difference between H3 and H4 that's caused by the difference between the velocity going to 0 or the velocity not going to 0. So we're going to do all that. Now we're going to try to find all these heights. We're going to assume that the velocity and the pressure do not depend on the radial position. So if the pressure is, 120 kPa right here, it's 120 kPa that entire span of the pipe right there at that particular location. So let's go ahead and calculate H1. That's pretty easy. You might even want to turn off the video just to do a quick check on yourself, but it's pretty clear that H1 is going to be simple. So we know what P1 is. P1 is 120. We also know that P1 minus P0 is going to equal rho GH1. So that's going to be the difference between P1 and P0. And so we just plug the numbers in. So we've got 120,000 minus 101,000 equals rho is 1,000, because we said it's water, kilograms per meter cubed. G, of course, 9.81 meters per second squared. And then H1 is what we're after. So we're going to solve all that for H1. Get H1 is equal to 1.9 meters. So that first height is 1.9 meters. That tells us that the pressure at position 1 is 120 kPa. So if we didn't know P1, this would be how you'd find P1. You'd put a tube in, you'd look at that height of H1, and you would calculate then that P1 is equal to 120 kPa. All right, so now we're going to go after H2. H2 is going to be, of course, the same formula for pressure, P2 minus P0 over rho G. That's not going to change. That's the formula for just the water in the tube. So you got the tube, and the pressure at the top of the tube, the water is P0 because it's open to the atmosphere, and the pressure here is whatever P2 is. And the question is, what is P2? Well, we can figure that out using the Bernoulli equation. So P1 over rho plus V1 squared over 2 plus GZ1 is equal to a constant, which of course is equal to, we can actually figure out what that constant is if we want. In order to define that constant, we would have to come up with a value for Z1. So what height do we want to make Z1? Well, of course, you can make it anything you want. Put your axes anywhere you want. I'm going to put my axis so that Z1 equals 0. So I'm just going to let Z1 be position 0 so that I can zero that term out. So I've got P1 over rho plus V1 squared over 2 is equal to what? So that's equal to a constant, the Bernoulli constant for this flow. And so I got 120 kPa divided by 1,000 kilograms per meter cubed plus 12 meters per second squared over 2. And got to be careful here. It should just be regular PA. So it's going to be 120,000 divided by 1,000. So it's going to be 120 on this term plus this 144 divided by 2. So that's just 192. I guess the units for that are meters squared per second squared. Meters per second squared, since that's what the units of this thing are. So that's my constant, 192. So then I can apply that same thing to the second equation for position 2, because that's what it's constant in the flow. So P2 over rho plus V2 squared over 2 is also equal to 192. Z2 is equal to Z1, which equals 0, because Z2 and Z1, they're in the same position in the pipe. So there's no change in height from 1 to 2. So the only thing that changes is that V2 is equal to 0. So that's what I'm going to do. So V2 is equal to 0. That means P2 over rho equals 192, which means that P2 is equal to 192 thousandths, and that's newtons per meter squared. So that's my pressure at 2. Now I can use that to get my H2. So my H2 is equal to 192,000 minus 101,000. So that's P2 minus P0 over 1,000 kilograms per meter cubed, of course, 9.81 meters per second squared. These are all newtons per meter squared up here. So I get 9.28 meters. So H2 is quite a bit higher. It's 5 times as big, almost 4 and a half times as big as H1, because this pressure is much, much higher at P2 because the velocity has dropped to 0, and that's caused a large increase in pressure as that velocity has stagnated, what we call stagnation velocity. We'll talk about that again in a second. All right, so now I want to move on to position 3, but that same Bernoulli constant still applies. So I have P3 over rho plus V3 squared over 2 plus GZ3 is equal to 192. I'm going to pull the picture back up just so we recall exactly where I'm talking about here. Well, here's the picture I had in my notes. So position 3 is farther up the tube. We know that the height difference between positions 1 and 2 and positions 3 and 4 is 0.4 meters. So we're at a different location farther up the pipe. And so we'll now try to figure out how that affects everything. So that's where we are. So this Z3 is going to be 0.4. So we got to have that in here. So we've got P3 over rho plus V3 is going to be, again, 12, because that third opening is facing downward. So there's no change in velocity. The flow is just going right by that pipe. So G, and then this is 0.4 meters here, equals 192. And I said V3 is still 12 meters per second because the third opening was one that went just straight down. And it's the fourth opening that has this thing that faces the flow. So this is 3 and this is 4. So the flow is going right by here. There's no velocity change. So that's going to go in there, and then I can solve all of that for P3. V1 equals V3 equals 12 meters per second. So P3 is equal to 116,000 newtons per meter squared. All right, so now I'm finding my height for 3. So once again, H3 is equal to P3, so 116,000, minus P0, open to the atmosphere, divided by rho and G again. So when you plug all those numbers in, you get H3 is equal to 1.53 meters. So slightly less than H1 because it's higher, right? So some of the pressure now has decreased because the fluid has gone up to a higher elevation. And according to the Bernoulli equation, that means that, that's going to add to this. So if this is going to all equal a constant, a higher elevation is going to have to mean a lower pressure or a lower velocity. Well, velocity stayed the same, has to because of conservation of mass. So therefore, the pressure must have dropped because the elevation is higher. All right, so now we're going to look at P4. So we have P4 over rho plus V4 squared over 2 plus GZ4 is equal to 192. Same Bernoulli constant. V4 now equals 0 because, again, we have one of these tubes that's facing the flow. So the velocity here is going to be 12 meters per second, but right at the entrance, the velocity is going to be equal to 0 because it can't. This tube it's hydrostatic. There's no fluid flow in the tube. It's balanced on pressure. So V4 at the entrance is going to be 0. So that means that P4 over rho plus G 0.4 meters, the elevation is the same as 3, is equal to 192. So we crank all that around, and we get that P4 is equal to 188,000 newtons per meter squared. And so H4 is 188,000 minus 101,000 divided by rho and G, and you get H4 is equal to 8.87 meters. So it's less than H2, obviously quite a bit greater than H3 as we expected, because once again, that velocity going to 0 is going to increase that pressure quite a lot due to the Bernoulli effect there. So finally, I'm just going to show you a little picture of the final heights here. So we had 1.9 height for the opening 1, which had the opening facing downward, and so no velocity loss there, 12 meters per second velocity, low pressure, but higher than atmospheric pressure, so it still has a positive H. Then this one is really large because the velocity drops to 0 at the entrance to pipe 2. We get this big change. This one drops a little bit more because it's higher in elevation than H1 is, so that pressure is less here up at this higher part of the pipe. And this pressure here is also much larger than H3. The H4 pressure is high, so you get 8.87 meters of height. It's interesting to note that this height of 4 and this height of 2 in an absolute Z scale are the same. So H2 equals H4 plus delta Z within 0.01 as I've done the calculations, which is simply a matter of a rounding error. So these in fact stay the same. So the total amount of head pressure in the system, or the amount of energy in the system, hasn't changed. It's just kind of it's reduced its pressure, but it's increased its elevation. But the total height actually between these two columns is actually identical to each other, even though excuse me, they are not the same here, but because this one is actually 0.4 higher than this one where it starts. These two are not quite the same. So they look kind of similar too, but they're not. This one is actually will drop more as height goes up.